Good morning, we are from CEB1072, Chemical Engineering Thermodynamics, one of University Technology Petronas. The problem statement of our integrated project is to generate electricity to meet economy and population growth. The location is at Lumuk Neighbor Base, Perak, and the requirement or aim is to produce 500 megawatt electricity and utilizing low sulfur grade coal. This is how a combined cycle plant works to produce electricity and capture waste heat from the gas turbine to increase efficiencies and electrical output. The first step is gas turbine will burn fuel. The second step is heat recovery system captures exhaust. And then lastly, the third step is steam turbines deliver additional electricity. The details of each step is written and you may refer to them by stopping the video. In front of us, you can see a gas turbine which weighs approximately 400 tons and the gas turbine is where the fuel is burned to spin the generator. Gas turbine is the heart of the power plant. It compresses the air and mixes the air with fuels which is ignited to spin the turbine blades. The spinning energy is then converted to electrical energy. Behind the turbine is another key component, which is the heat recovery steam generator, HRSG. Its functions to capture exhaust from the gas turbine, or otherwise, the exhaust will escape through the exhaust stack and creating steam. The generated steam is then sent to the steam turbine and generate even more energy. The main steam piping delivers high temperature and pressure steam from the HRSG back to the steam turbine. The steam turbine uses steam to spin the generator, creating additional powers. The working principle of steam turbine is same as the gas turbine and it helps to produce more electrical energy.
So now let's talk about our design. So as you can see in the screen, this is our schematic diagram. This is a combination of a gas cycle and steam cycle, where a gas cycle consists of 7 gas turbines, 1 compressor, 1 combustion chamber, and then 1 generator, and it linked with 1 heat exchanger. Steam cycle got 1 steam turbine, 1 condenser, 3 pumps, as well as 1 generator. So there are a few general assumptions towards our calculations, such as all devices are steady flow devices, as flow rates are constant throughout the gas and steam cycle accordingly. All of the gas turbines and steam turbines are well insulated. There is no heat loss to the surroundings. It also a stationary system, so no change in kinetic energy and potential energy. It is a constant pressure in combustor and condenser. There is no leakage between pipelines, fixed mass and closed system. So next, this is the criteria of the material streams. For all the gas cycle streams, we consider air as an ideal gas. For the steam cycle, which out from the pump is the stream 6 with compressed liquid, go into the heat exchanger, and then out from it is the stream 7 with superheated vapor with high pressure temperature, and then out of the steam turbine is stream 8 as saturated mixture, and then it goes into the condenser and out as a compressed liquid of stream 9. This is the general energy balance for steady flow devices. From references, we deduce the energy in will equal to energy out, and all the derivation as you can see on the screen. And this is the result. The work out from the gas turbine is 490,000 kilowatt. Work in by compressor is 33,000 kilowatt. The work out from the steam turbine is around 45,000 kilowatt, and work in by pump is around 1,800 kilowatt. Total power is combining the net power from gas cycle and steam cycle to get approximately 500 megawatts. So the objective of this study is achieved. Other than that, we have question requirements such as the amount of coal, around 60 kilogram per second. Overall thermal efficiency is 56%. The steam generated out of the heat exchanger is 1,600 meter cube per kilogram, and the backward ratio 0.067.
Let's take an example of calculation from energy balance in heat exchanger where we can find the value of T5 as 1064.5 Kelvin.
Hi, my name is Sofia, and here I'll be presenting the discussion content in our project. Combined gas steam power cycle design is a combination of Brayton cycle and Rankine cycle. Both cycles undergo 4 processes which are isentropic compression, isobaric heat addition, isentropic expansion, and isobaric heat rejection continuously in a cycling mode. Carnot cycle, which is a reversible cycle, is not suitable to idealized power cycle due to some factors such Carnot cycle cannot evaluate phase changes occur in a steam cycle. In our project, we need to design a power production plant which can be categorized as the actual power. Therefore, due to irreversibility and pressure drop that may happen throughout the cycle, some changes may occur as can be seen in the diagram shown where the dashed line represents the actual cyclic processes. Isentropic efficiency is one of the key points that differentiate between actual cycle and ideal cycle, where through this we can estimate the actual power generated by the turbine. Meanwhile, we can also find the work consumption by the compressor and pumps by evaluating these isentropic efficiency and property tables. However, there might be some values such as enthalpy that need to be determined first before calculations of work started. Therefore, we can use isentropic relation as the solution by assuming some conditions that fit the relation. The project requires the calculation of the network production, and the value obtained is approximately equal to 500 megawatt, which successfully achieved the aim of the project. Besides, the amount of coal used as fuel also need to be calculated, where we get an amount of 60 kg per hour, which is suitable for the power production capacity. The project also requires the calculation of thermal efficiency, where we have 51.2, 56, and 4.8% for the gas cycle, combined cycle, and steam cycle respectively. From this, we can see that the steam cycle produces much less work compared to the gas cycle. The back-work ratio also being calculated, where it indicates the performance of the cycle. Our design combined power cycle have a good performance, and it has a very low ratio of 0.067.
For the conclusions and recommendations, we can conclude that the net power generation is 506,556 kilowatt, which is approximately equal to 500 megawatt. This value meets the aim of the designing combined gas steam power plant cycle. The total amount of coal used as fuel is 59.44 kg per second in the combustion chamber to produce a hot flue gas in order to turn the turbine. The overall efficiency of combined power cycle is 56.8%, which is a good efficiency. The combined power cycle design has a value of 0.067. Now, moving on to the recommendation, please pause the video to read on the justification. We recommend to use more gas turbine with a design that can uphold higher inlet temperature, use more powerful gas turbine that will produce higher amount of work with higher isentropic efficiency. Next, we also recommend to add a heat exchanger before combustor to readily heat up the air from the outlet compressor using exhaust gas. And last but not least, we recommend to add on another cycle, which is a secondary cycle of low pressure steam cycle. That is all from our group. Thank you for watching.